The mechanism is a device that was built over 2,000 years ago. It's an ancient Greek astronomical computer, and it maps the stars. It challenges everything we thought we knew about technological history. A handful of corroded bronze gears forced scientists to rewrite the story of human innovation. It predicted cosmic events with precision, and there's a haunting mystery. That kind of brilliance vanished from the Earth for more than a millennium. So what does a forgotten relic tell us about our own civilization's legacy? Near that small island had a secret. It kept it for 2,000 years. Then in the spring of 1901, a crew of Greek sponge divers were working there. They were in the deep water off, and they saw something. At about 50 meters down, the light was dim, but they could see the shape. It was a wreck, a Roman cargo ship. It went down in the 1st century before the Common Era. These divers, they had the old suits, the air pumped down through hoses. They started bringing things up. It was dangerous work. They recovered statues, bronze and marble all twisted from the sea. They found glassware, they found coins. It was like a museum down there, a whole shipment from Greece to Rome. And they also brought up this other thing. It was a lump, bronze and wood about the size of a big book. It was covered in crust in marine growth. It looked like a rock, just a piece of the seabed. On land, the archaeologists saw the statues, the glass. Then they saw this thing. It was ugly, crumbling. It was a curiosity. Maybe just scrap metal. They cataloged it. They put it aside. Its real nature, you couldn't see it, not then, so it sat. For almost 50 years it sat in a storeroom in Athens, in the National Museum. It was a puzzle box but forgot. That first reaction, that dismissal, it means something. The world wasn't ready. The idea of a computer from the ancient world, it was unthinkable. So this mechanism, this piece of engineering, it stayed silent. Its gears were locked, stuck in that calcified tomb. And above, the 20th century moved on. It had its own technology, its own revolutions. Everything was in place. But the main thing, the device, it was still hidden, shrouded in stone. Its script was written in mathematics, a language no one could read. They gave it a simple museum number. Just a lump of corroded bronze and wood. They logged it as possibly an astrolabe, a navigational tool, and then they put it away. But a year later, in 1902, an archaeologist named was looking at the fragments. He was examining the crust and he saw something. There in the limestone-like corrosion were outlines, gear wheels, not just one, several. They were precise. They were toothed. This wasn't a statue. It wasn't decorative art. This was a machine, and the sight was impossible. According to every history book, technology this sophisticated didn't exist in the ancient Greek world. Complex gearing was a medieval invention from clockmakers centuries later. But here was the proof, physical proof, staring back at him from a 2,000-year-old shipwreck. The discovery created a lasting puzzlement. For decades, the mechanism was a ghost, mentioned in papers, argued over in conferences, but no one could explain it. It was an anomaly. A piece of advanced technology that had fallen out of its proper time into the wrong chapter of history. It just didn't fit. How do you categorize an object that rewrites the timeline you're using to categorize it? That initial confusion wasn't a failure. It was essential. It framed the only question that mattered. What was this device actually for? And more importantly, who had the knowledge to conceive of it, to craft those tiny bronze teeth, to assemble this cosmic puzzle box? The term computer wouldn't be applied to it for many more years by a researcher named Price, but the seed was planted right there. In that storeroom, they were looking at a message, a language of mathematics and astronomy written in metal. And for a long time, no one knew how to read it. For 50 years, that mechanism was just a stone shell. It kept its secret. Then in the 70s, we got a way to look inside. A physicist, Price, worked with a Greek radiologist. They used early X-ray and gamma-ray imaging, and they saw something they didn't expect. The crust fell away in the scans. It showed the outline of a machine, a precise assembly. At least 30 interlocking bronze gears, some were very small. They had intricate triangular teeth cut by hand over 2,000 years ago, and they weren't just stacked. They were arranged in a system, a complex, purposeful system. It was architecture, a miniature bronze universe. But the most shocking thing was at the heart of it. The scans showed a differential gear. To see why that's astonishing, think of a car's rear axle. A differential lets two wheels spin at different speeds when you turn. It's a foundational piece of modern engineering. It was reinvented in the 16th century for clocks and then for cars, but here it was, in a device that sank before the birth of Christ. This wasn't an accident. It was intentional, brilliant engineering. That differential gear solved a celestial puzzle. The moon's orbit isn't a perfect circle. Its speed varies. It has an anomaly, The ancient Greeks knew this, and with this gear the mechanism could model that, the irregular motion, the speeding up and slowing down. It could do it with breathtaking accuracy. It could simulate the cosmos. That internal architecture changed everything. It turned the bronze lump from a curiosity into a revelation. This wasn't a simple calendar, it wasn't a sundial, it was a mechanical computer. Its gears were programmed, through their sizes and their connections. They could calculate the phases of the moon, they could predict eclipses, years in advance. The sophistication was staggering. It meant something. The level of engineering, the astronomical understanding needed to build this. It didn't emerge in medieval Europe. It was alive in the Mediterranean world over 1,000 years earlier. The scans forced a reassessment, a complete and humbling one. What else did they know? What other chapters of human ingenuity are lost, sitting on a seabed, in a forgotten storeroom, waiting to speak? This was a machine you were meant to use, to hold, to turn. There was probably a small handle on its side, a crank. And when someone turned it, a priest, a scholar, someone with money, the bronze universe inside would start. Gears would mesh. Pointers would begin to move across these dials. On the front, a large circular display showed the sky. The stars, the sun and moon, and the 5 wandering stars, the planets, Mercury, Venus, Mars, Jupiter, Saturn. Their positions against the zodiac were shown, calculated by those turning gears. It was a portable planetarium, a miniature cosmos in your hands. But it did more than that. It was a master of time. One of its key cycles was the Metonic cycle, 19 solar years, exactly 235 lunar months. After that time, the moon's phases repeat on the same calendar dates. This was vital for calendars, for planting seasons, for religious festivals. The mechanism tracked this 19-year cycle precisely, a long-term astronomical calculation. Its most dramatic function was predicting eclipses. On a separate dial, probably on the back, was a spiral scale. As you turned the crank, a pointer moved along this spiral, showing when the next eclipse would happen. Lunar or solar, it didn't just give a date. The inscriptions suggest it predicted the eclipse's characteristics, its direction, its color, maybe the weather omens tied to it. That knowledge in the ancient world held immense power. To know when the sun or moon would be swallowed by shadow was to seem in tune with the gods. Perhaps the most stunning feature was its model of the moon's motion. The moon doesn't orbit at a constant speed. Its path is elliptical, so it speeds up and slows down. This irregularity is called the first anomaly. The mechanism's differential gear assembly simulated this perfectly. The pointer for the moon on the front dial would actually move faster and slower, mirroring the real moon's dance. So the Greeks weren't just tracking positions, they were modeling physics. They encoded an understanding of celestial mechanics into bronze, centuries before described the laws of planetary motion. So what was it for? Practically, it was a tool for planning the harvest by the moon, for setting the date of the Olympic Games, for an astrologer casting a horoscope with new accuracy. But to call it just a tool misses the point. This was a model of the universe, a working theory of everything they knew, made in metal and mathematics. When that hand turned the crank, it wasn't just moving pointers. It was animating a philosophy. It was proving the cosmos wasn't a chaotic mystery, but a comprehensible, predictable machine. And that idea that the universe operates by knowable rules, that's the foundation of all science. The mechanism wasn't just predicting eclipses. It was predicting the scientific revolution itself, more than 1,000 years early. A machine is only as powerful as its instructions. The mechanism had bronze gears that were silent, but its casing was. There was a voice etched across it, in letters smaller than a grain of rice. Over 3,500 Greek characters have been read, and they form a complete user manual from antiquity. It wasn't decoration. It was a technical guide, engraved right onto the device. It labels the dials. It explains the astronomical cycles it calculates. You see the words Saros cycle and cycle, which are precise eclipse and calendar periods. One inscription even says the spiral of, pointing to the dial that tracked the orbit of Saturn. Those tiny words change the object. They turn it from an abstract puzzle into a practical tool meant to be held and understood and operated. Someone 2,000 years ago was expected to read this manual and use this computer. The text includes something called "that was a star calendar." It linked the rising and setting of constellations with predictions for seasonal weather, which was useful for farmers and sailors. So this wasn't just for philosophers in a library. It connected the cycles in the sky to the practical rhythms of life on the ground. The existence of this manual tells us something. It assumes a user, It assumes a person who could read Greek and understand basic astronomical terms. This device was built for a market, for a clientele. It implies a workshop, a tradition, a school of thought that could make such intricate objects. The inscriptions are the final piece of evidence. They silence any remaining doubt. This was a manufactured product of Hellenistic science, a working model of the cosmos, sold with a warranty written in bronze. When you read those painstakingly engraved words, you're not just looking at a description of gears. You're listening to the thought process of the engineer. You're seeing the world through their eyes, a world so ordered and predictable that its movements could be captured in metal and explained in text. The mechanism itself is the answer to a calculation, but the manual is the answer to a deeper question. It proves the makers knew exactly what they had built, and they built it for a world they believed was ready to understand it. Those tiny gears weren't just parts, they were arguments made of bronze. Every time a wheel turned, every time teeth meshed, it was a physical statement about how the universe worked. This thing is a library of Greek astronomy, but you can hold it, you can set it in motion. It takes the abstract work of someone like Hipparchus and it makes it solid. Hipparchus of Rhodes in the 2nd century BCE, he was looking at the moon's path. He saw its speed wasn't constant. To explain that, he came up with a model, an epicycle. Picture a small circle, and its center moves around the edge of a bigger circle. The moon goes around that small one. That dance of circles, when you trace it out, it creates that speeding up and slowing down we see. That's a beautiful idea on paper, but inside this mechanism it becomes metal. Researchers think a specific set of gears, a differential gear and a train of smaller ones, they physically recreate that epicyclic motion. Hipparchus's theory of circles wasn't just a sketch. It was a blueprint, and someone built it. That's the leap here. It takes philosophy off the scroll and forges it into a working model. The device shows a complete cosmos with Earth at the center, motionless. Around it on the front you have pointers for the sun and the moon and the 5 planets. They move against the zodiac. Their motions are complex, circles within circles, but they're predictable. The mechanism says the cosmos isn't a realm of capricious gods, it's a machine. A magnificent, orderly machine. Its rules are mathematical so they can be known. That belief that the universe runs on laws we can understand, that's the foundation of all science. This mechanism is that belief made tangible, its confidence cast in bronze. The people who built it looked at the bewildering dance of the sky and they didn't see chaos. They saw clockwork. They heard a rhythm in the silence of space, and they built something to keep its time. That might be its most lasting message. It whispers across 2,000 years that the desire to understand, to model, to predict, that's not a modern invention. It's a human impulse. As old as the stars, just waiting for the right hands to give it a shape. The person who made it is still unknown. We can follow the ideas, but the hands that work the bronze are lost. The craftsmanship itself is a kind of signature. Every gear was cut from a flat sheet of bronze. The dozens of teeth on each one were filed by hand to a uniformity that seems almost impossible. The tolerances are astonishing. The gear teeth are spaced within a fraction of a millimeter. This wasn't mass production. This was bespoke engineering. The work of a master who knew that a single flawed tooth could throw the whole cosmic calculation off. The front and back plates, also bronze, were engraved with fine scales. Hundreds of tiny characters. The whole assembly was fitted into a wooden case. A compact universe about the size of a shoebox. That level of miniaturization, that integration, it points to something beyond a lone tinkerer. It suggests a dedicated workshop, a tradition of fine instrument making perfected over generations. So where would a workshop like that exist? Historians look to the great hubs of the Hellenistic world. Rhodes was a center for astronomy and engineering. Alexandria, with its library, was a melting pot of science and craftsmanship. Either one is a plausible home, which leads to the question of the maker's identity. We have no name, but we have a shadow from history that fits. The legendary Archimedes of ancient texts describe him building intricate models of the heavens, celestial spheres that showed the motions of the sun, moon, and planets. When the Romans sacked, the general is said to have taken just one thing as a personal prize, a planetarium built by Archimedes. So the mechanism could be a descendant of that lost technology, maybe built by a follower in the decades after Archimedes died. It's a compelling thought. Whether it was directly inspired by him or not, the builder was a unique fusion of talents, an astronomer who could calculate the complex cycles of the sky, a mathematician who could translate those cycles into gear ratios, and an artisan with the skill to turn those ratios into a physical working reality. This individual stood at the peak of their civilization's technical ability. Their name is lost, erased by the centuries, but their voice isn't lost. It speaks in the quiet click of bronze teeth engaging, in the smooth sweep of a pointer across a dial inscribed with stars. It's the voice of a forgotten genius who looked at the cosmos and dared to build a clock for it. The question is, who used this clock? Who turned the handle and watched the pointers? There's a debate that's gone on for years. A tool, a teacher, or a talisman? It was probably all three. In the ancient mind, those things weren't separate. They were threads in the same fabric. Take the eclipse predictions. For a sailor on the Mediterranean, knowing a lunar eclipse was coming could help with navigation on a dark night. For a farmer, it marked a time in a celestial calendar tied to seasons. But an eclipse was also a powerful omen, a moment when the gods seemed to speak through the shadow, predicting. It wasn't just practical. It was a sacred act, a demonstration of harmony with the divine order. So the same function served navigation, agriculture, and religion all at once. Then there are the planets. Their positions against the zodiac were the raw data for casting a horoscope. Astrology wasn't mere superstition then. It was a sophisticated system linking the heavens to human life. A wealthy patron paying for a personal horoscope would want accuracy. This device could provide it far more reliably than manual calculation. That suggests a clientele of elites, priests, or royal advisors. For them, such knowledge was power. Yet the beautiful, moving model of the cosmos also served a philosophical purpose. For a student in a library, seeing the gears turn and replicate the irregular dance of the moon made abstract theory tangible. It was a teaching machine, a three-dimensional diagram proving the mathematical elegance of the universe. Its very existence points to a final purpose, though: prestige. The materials, the staggering craftsmanship, the deep knowledge required to build it. This wasn't a common object. It was an artifact of luxury and intellectual status. Owning it or having access to it in a temple or royal collection was a statement. It said, "We do not just observe the cosmos, we comprehend it. We have captured its logic in bronze." It embodied the Hellenistic ideal where science, art, and power were intertwined. The mechanism wasn't merely a calculator. It was a symbol, a compact working emblem of a civilization's confidence. Its desire to master time, predict the heavens, and hold a miniature, ticking universe in its hands. This machine was brilliant, but it was a dead end. Its technology disappeared from the Earth for over 1,000 years. So what happened? How could something that advanced be lost so completely? The mechanism itself didn't fail. The civilization that built it failed. The Hellenistic world, that network of Greek kingdoms after Alexander, was a golden age for pure science and intricate craft. It was a world that valued that kind of deep theoretical work. But that world was ending. The Roman Republic was rising, and then the Empire. The Romans were phenomenal engineers, but their genius was practical. They built aqueducts and roads and siege engines. Their focus was on conquest, on administration, on monumental construction. They admired Greek science, they collected its artifacts as trophies, but they didn't seem to nurture that same kind of specialized, abstract engineering. The delicate ecosystem you needed to make a device like this, the astronomer, the mathematician, the master all working together, that began to wither. The specialized workshops probably disappeared. The knowledge became concentrated in just a few hands and then in none. Then there were the fires. The Great Library of Alexandria, the greatest store of knowledge in the ancient world, suffered a series of devastating losses over centuries. The full story is complex, but these events symbolize a broader decay. Scrolls burned, texts were lost. Entire lineages of thought, including the intricate manuals and designs for devices like this one, turned to ash and were forgotten. The technology didn't just fade, it was severed at the root. Without a living tradition to teach it, without text to reference, the ability to recreate such a machine just evaporated. The mechanism became a ghost in the historical record, an anomaly with no ancestors and no descendants. Its loss is a stark lesson in the fragility of knowledge. It shows that technological progress isn't a straight, inevitable line upward. It can be a fragile thread, easily broken by shifting priorities, by conflict, by the slow erosion of time. For over 1,000 years, the very idea of a geared computer was unimaginable. The mechanism slept on the seabed, and the world above forgot that such a thing had ever been possible. That silence, that gap of centuries, is maybe the most haunting part of the story. It asks us an urgent question about our own civilization. What are we building today that could be just as fragile? What threads of knowledge are we holding that, if we drop them, might take a millennium to pick up again? The corroded bronze had been silent for a long time. That was going to change. In the early 2000s, a group of scientists and historians put the mechanism under a new kind of light. They used a technology its makers couldn't have imagined. X-ray computed tomography. It's a CT scanner, but much more precise. They could see through 2,000 years of crust, layer by layer. They saw the gears. And they saw the impressions of gears that had dissolved completely. They read inscriptions that had been invisible, buried inside. For the first time, they could map the whole internal structure in 3 dimensions. That was the pivotal moment. It wasn't about fragments anymore. It was about seeing the complete machine, reassembled in digital space. A researcher, Tony, and his colleagues took that 3D data. They did something remarkable. They built a virtual model. They could simulate every gear's motion, trace every pointer's path. They could turn the crank on a screen and watch the ancient cosmos move. The digital model confirmed some ideas, it shattered others. It showed a stunningly complex system on the device's back, a spiral dial for tracking eclipses, with a tiny subsidiary dial that worked as a 4-year turn counter. A calendar inside a calendar, but the deepest confirmation came from the front. The scans showed the remnants of a system to display the planet's motions, not just their positions, their retrograde motion, that apparent backward loop planets make. The Greeks explained it with epicycles, and the mechanisms gearing physically modeled it. The virtual reconstruction proved this function wasn't just possible, it was engineered into the heart of the device. This wasn't just an astronomical calculator anymore. It was a comprehensive orrery, a model of the entire known solar system. The 3D models did more than confirm functions. They answered a lingering question about quality. Were these gears crude or were they masterful? The scans showed the answer. The teeth were hand-cut, with a consistency that's hard to believe. The spacing between them varied by less than a human hair's thickness. This was precision engineering of the highest order. Then the virtual reconstructions led to physical ones. Teams around the world used the scan data to build working replicas, from laser-sintered plastic to handcrafted bronze. These modern recreations finally let people do what no one had done for 2,000 years. They could hold a facsimile, turn the handle, and witness the dance of the gears as it was meant to be. The experience is humbling. You're not looking at a static artifact in a case. You're operating a bridge. A bridge built from 21st century silicon and software, reaching back to grasp the genius of Hellenistic bronze. The mechanism's voice, muffled for so long by salt and time, was finally clear. And what it said was more sophisticated, more beautiful, and more revolutionary than anyone had dared to dream. The real proof of its genius is on the back. A spiral dial was there, and it held the key to predicting one of the most awe-inspiring things in the ancient sky, an eclipse. This wasn't just a calendar marking a date. It was a complex algorithm, but written in gears. It could forecast eclipses decades into the future. The system used 2 cycles that ancient astronomers discovered. The first is the Saros cycle. That's about 18 years and 11 days. After that period, the Sun, Earth, and Moon go back to almost the same geometry, so a similar eclipse happens, but it's not perfect. The alignment is a little off, so where you can see the eclipse on Earth shifts. To correct for that drift, the mechanism used a second, longer cycle. That's a triple Saros, about 54 years and 1 month. After that triple cycle, eclipses not only repeat, but they become visible from roughly the same part of the world again. The back dial physically modeled these cycles, one inside the other. You'd turn the main handle, and a pointer would travel along this spiral groove. Each coil of the spiral was 1 Saros cycle. The pointer's position showed you the month an eclipse was due, but it did more than that. Inscriptions around the dial gave you details. They told you if the coming eclipse was solar or lunar. They suggested characteristics with words like blood red, maybe describing the coppery color of a total lunar eclipse. That changed the device. It turned from a calculator into a kind of prophet. It took chaotic, fearsome events in the sky and made them scheduled. Understood, next to this big spiral was a smaller dial, a subsidiary one. That one tracked the 4-year cycle of the Panhellenic Games, which included the Olympics. That connection is profound. It linked the cosmic clockwork directly to the most important cultural and athletic event in the Greek world. It meant the rhythm of the heavens and the rhythm of human celebration were part of the same system, a measurable one. To build this predictor, the makers needed data, centuries of it. They almost certainly used meticulous records kept by Babylonian astronomers. For generations, they logged every eclipse they saw. Greek thinkers like Hipparchus and others, they analyzed these patterns. They distilled them into the mathematical cycles of Saros, and the mechanism's brilliance was to take that abstract, hard-won knowledge and automate it. You didn't need to be a master astronomer consulting fragile papyrus scrolls. You just turned a crank. The machine consulted the collective memory of centuries. It delivered a prediction with the quiet authority of moving bronze. It made the long-term order of the cosmos tangible. It offered a kind of comfort, a promise that even the most dramatic celestial events weren't random acts of the gods. They were part of a grand, predictable cycle. A cycle human minds could grasp and human hands could replicate. The front dial had another purpose. It wasn't just for the sun and moon. It was meant to show the planets, the 5 wanderers, Mercury, Venus, Mars, Jupiter, Saturn. Their names are right there on the inscriptions. For a long time, people thought that was just an aspiration, that the machine couldn't actually do that. The planets move in these complicated loops. They slow down, they stop, they go backwards, retrograde motion. The Greeks saw that as a puzzle. Their solution was the epicycle, a small circle on a bigger circle. That geometry creates the loops. It's a theory of circles. The mechanism tried to build those circles. The scans show a lost system of gears inside, an epicyclic system. A gear on a moving gear to physically produce that path. They built the theory in bronze, and the challenge of that, each planet has a different timing. Mercury's cycle is 88 days. Saturn's is 29 years to model all 5 in one box with interlocking gears from one single crank. The precision needed for those gear ratios. The space for all those nested systems, it's immense. This was the goal, a complete cosmic simulator, a model of the known universe, to turn the handle and see Mars begin its backward loop in Leo. At the right time, that would be a revelation, to feel the logic of the cosmos clicking into place. This pushes it from a calculator into something else, a statement that the bewildering sky isn't chaos, it's mathematics in motion, and if you can understand the math, you can build a mirror of it. The mechanism didn't just appear. It came out of a particular time, a specific place. The Hellenistic period, those 3 centuries after Alexander. His conquests built an empire, but they also built a kind of network. A network for ideas. Greek thinkers suddenly had access to all the old knowledge from Egypt, Mesopotamia, Persia. They weren't just gathering treasure, they were gathering data. In Alexandria's library, you'd find Babylonian star charts right next to Egyptian geometry. It was a fusion, a melting pot for the mind. And in that setting, science wasn't some quiet study. It was a spectacle. Kings and cities competed for prestige, funding it almost like a contest. An ancient space race, but for figuring out the cosmos itself. On Rhodes, Hipparchus was cataloging stars, noticing the equinoxes slowly shifting. In Alexandria, Aristarchus was working out the distances to the sun and moon. He even suggested the Earth might go around the sun. Mathematicians like Euclid were writing the rules of geometry, which became the language for plotting planets. And engineers were building things, water clocks, pneumatic devices, figuring out mechanics by hand. This was a culture that didn't only want to think about the universe. It wanted to build a model of it. The lines we draw now, between astronomy and astrology, between math and magic, between philosophy and engineering, those didn't really exist. A device that predicted an eclipse helped the sailor and the priest. A set of gears modeling planetary motion was a scientific instrument, but also a way to show divine order. The mechanism is the pure result of that blended world. Its eclipse predictions use the Babylonian Saros cycle. Its gears are built on Greek theories of epicycles. Its calendar might pull from Egyptian traditions. It's a physical fusion, Eastern data and Greek theory, made solid by incredible craftsmanship. This object is what happens when a civilization hits a peak of cross-cultural curiosity. When it has the resources, the patronage, the sheer nerve to ask not just how the heavens work, but whether you can hold a working copy. The Hellenistic world was that incubator. It had the raw knowledge, the technical skill, the philosophical hunger to make that leap. And then within a few generations, that world started to fall apart, leaving this one device behind, a time capsule. A single, miraculous piece of its lost brilliance. But was it the only one, the only survivor? The writings from that time point somewhere else. The mechanism probably wasn't unique. It was part of a category. Classical authors talk about similar things, and they talk about them with a kind of casual tone. Cicero, in the 1st century BCE, writes about a bronze globe. It was brought to Rome by the general after was sacked. He says Archimedes made it. And it showed the motions of the sun, the moon, and the 5 planets. It was so accurate it could show eclipses. That's not a vague legend. It's a direct description of something that sounds a lot like our mechanism. Other writers, Ovid, and they mention these intricate models of the heavens too. They were known, at least among the educated elite. They were collectible marvels. The fact these texts mention them so plainly means they weren't unimaginable miracles. They were recognized achievements. Rare but recognized. The sophistication of the device itself argues against a lone genius working alone. Its design is too specialized, too refined. Those gear ratios come from deep astronomical calculation. The compact assembly shows a mastery of miniaturization. That level of integration doesn't come from a vacuum. It comes from a workshop tradition, from trial and error, from masters teaching apprentices. It suggests a lineage. Instrument makers who perfected their art over generations. So where are all the others? The fate of most ancient technology is to vanish. Bronze was precious. When empires fell, when fortunes shifted, complex bronze objects were the first to be melted down, for coin or for weapons. A delicate geared mechanism had little value as a machine to a soldier or a metalsmith. It was raw material. Other devices might have been lost in similar shipwrecks. Still resting in the deep silt of the Mediterranean, waiting for another chance discovery. Many more just disintegrated. Wood rots, bronze corrodes. Without the perfect airless conditions of the wreck seabed, most would have crumbled to dust centuries ago. So this single artifact isn't a freak occurrence. It's a statistical miracle. A single page that survived from a vast, lost library of mechanical knowledge. It makes us reimagine the ancient world. Not as a place of static marble and scrolls, but as a place alive with moving parts, with ticking models of the cosmos, with a mechanical imagination we'd completely forgotten. The haunting question isn't why we found one, it's how many we've lost, and what their silent gears might have told us about the true height of that civilization's reach. To understand a machine, sometimes you build it yourself. That's what a group of researchers and engineers have done. They took the CT scan data and gave it solid form again. They built dozens of replicas, physical and digital, of the mechanism. One of the most famous was built by Michael Wright. He was a former curator at London's Science Museum. He worked for years. He meticulously crafted a fully functional model from brass. He used tools and techniques the ancient Greeks would have had. His hands-on work was a form of experimental archaeology. Every gear he cut, every shaft he fitted, was a conversation with the original makers. He wasn't just copying a diagram. He was solving the same practical puzzles. How do you pack dozens of interlocking gears into a box the size of a large book? How do you minimize friction so the mechanism turns smoothly for decades? How do you align all those astronomical cycles so the pointers on the dials tell the truth about the sky? Building it revealed the staggering ingenuity required. The differential gear assembly alone, which models the moon's variable speed, is a masterpiece of compact design. Wright's model, and others that followed, proved something crucial. The theoretical gear arrangements from the scans weren't just possible on paper. They were mechanically feasible with the technology of 2,000 years ago. A skilled artisan with files, drills, and a deep understanding of geometry could have created this. Today, the work continues with even greater precision. Researchers have created accurate digital simulations that can model every interaction. And using modern methods like 3D printing, enthusiasts and institutions have produced working replicas from plastic and metal. These tangible models do more than validate theory. They become portals. When you hold one, when you turn that small crank, you perform the same action a Greek scholar once did. You feel the gentle resistance of the gears. You watch the pointers begin their slow dance across the zodiac. You see the moon's marker speed up and slow down in its tiny loop. It transforms the device from a mysterious artifact behind glass into a living, ticking piece of history. It creates a connection no textbook or lecture ever could. You are, for a moment, operating the ancient world's most advanced computer. And in that silent dialogue between your hand and the bronze, you gain a profound respect for the minds that first imagined it. That one machine changes the story of progress. We had a timeline. The leap into mechanical computation happened in medieval Europe with the great tower clocks, the astronomical clocks. That was the start of complex gearing, but the mechanism breaks that. It moves the origin of precision mechanical calculation back over 1,000 years. This isn't a small change, it's a fundamental shift. It means the seeds of the scientific revolution, the idea of modeling nature with a machine, were planted not in the Renaissance, but in the Hellenistic world. Galileo, looking at the heavens in the 17th century, he was part of a tradition of observation that went back to Hipparchus. Mapping the planet's ellipses, he was working on a puzzle Greek engineers had already tried to solve in bronze. The mechanism shows that the intellectual foundation for all of it, the belief in a mathematically ordered cosmos you could simulate, was already there in antiquity. And that leads to a humbling thought. Technological advancement isn't a simple, steady climb from primitive to advanced. It's a landscape, with high peaks and deep valleys. A civilization can reach an astonishing summit of sophistication, and then that knowledge can be lost, buried by time, conflict, shifting priorities. The Hellenistic period was one of those peaks. Its fall sent the world into a long valley where the idea of a geared computer became unimaginable. For over 1,000 years, that summit was forgotten. Our modern assumption of linear superiority over the past is challenged by this. It asks us to see history not as a race we were destined to win, but as a story of brilliant flashes. Some burn bright and then vanish, leaving only echoes. This mechanism is the most powerful echo we have. It tells historians and archaeologists to look for sophistication in unexpected places, to question the neat timelines, to wonder what other peaks of human genius are still hidden, waiting to be found. It teaches that progress is fragile, that threads of knowledge can be broken, and that the greatest ideas are sometimes not the ones that change the world right away, but the ones that sleep for centuries, whispering their secrets only when the world is ready to listen again. The mechanism. It's this ancient machine, but it speaks directly to our world now, to code and silicon. It's more than just an artifact. It's a foundational idea in the history of computation. Researchers like he studied early calculating machines, and he saw a direct lineage. He looked at that one intricate differential gear, the one that models the moon's irregular orbit, and he recognized it. It's a piece of mechanical logic. That single component was lost, and then it was reinvented centuries later. It became the heart of early mechanical calculators. It even went into the rear axles of the first automobiles. This device, in every functional sense, is an analog computer. You provide an input by turning the crank. That motion gets processed through a fixed program, which is just the specific arrangement of the gear trains, their sizes, and it produces a precise output, the position of a planet. The timing of an eclipse. It's a machine built to compute. In our age, with invisible software and microscopic transistors, it's easy to forget. Computation didn't begin with electricity. It began with mechanics. The fundamental concepts are the same. You're processing data according to a set of rules to simulate a complex system. And the Greeks were simulating the most complex system they knew, the cosmos itself. So this corroded bronze box is a powerful metaphor. It reminds us that the drive to build machines that think, that calculate, that model reality, that's not a product of the 20th century. It's a much older impulse, a deeply human one. The mechanism stands as a quiet ancestor to every computer that followed, but it's a profound one. It challenges the story of the digital revolution. It suggests the roots aren't in the laboratories of the 1940s. They're in the workshops of ancient Rhodes or Alexandria. It asks us to see a continuous thread of ingenuity, from hand-cut bronze gears to silicon chips, all striving toward the same goal, to externalize our understanding, to build a working mirror of the world. Even with everything we've learned, the mechanism holds on to its secrets. After decades of study, we still don't have a complete blueprint. There's a major debate about the planetary gear trains. Different teams, looking at the same CT scans, have different ideas for how the lost gears drove the pointers for Mars, Jupiter, Saturn. The math works, but fitting it into that small wooden box is a fiendish puzzle. Those fragments are gone. We may never know the definitive layout. That's a gap in how we see this ancient cosmos. And the human story is just as elusive. No signature, no plaque. The maker's identity is a ghost in the gears. Was it one genius or a workshop, and who paid for it? A merchant, a royal court, a temple wanting to predict eclipses? We can only guess. The purpose might have been even broader. Some think about additional functions now lost. Could it predict tides for Mediterranean ports, track more than just the Pan-Hellenic games, local festivals, market cycles? The inscriptions we have hint at a device packed with information, a true multi-purpose computer for its age. Then there's the physical mystery. We have 82 fragments. They're precious, but there may be 1/3 of the original machine. 2/3 of it, gears, plates, text, is just missing. Did it break apart on the pieces scattered by currents, or were parts never on that ship to begin with? That question drives research in two directions now. In the lab, they use more refined imaging on the fragments, looking for microscopic text, construction clues the old scans missed. And in the deep water off, marine archaeologists go back to the wreck. They use robotic submersibles, mapping tools, scouring the seabed. The hope is simple, that another lump of corroded bronze is out there in the darkness. A fragment that could complete a gear train, confirm a planetary model, reveal a lost function. Each diving season is an act of faith, a belief the sea hasn't given up all the pieces. That's why the mechanism endures. It's not a closed case in a museum. It's a living question. Every unanswered detail, a missing gear tooth, a vanished name, fuels the next investigation. It keeps this 2,000-year-old computer from being just a relic. It stays an active participant in modern science, a conversation between centuries. And that conversation isn't over. The final word hasn't been found. The ship was a treasure vault, a floating one. Its cargo, it tells a story of conquest and taste and a world that was changing. When divers brought up those first artifacts, they weren't just recovering statues. They were pulling up a snapshot of an entire era. The hold was filled with luxury, exquisite bronze statues, philosophers, athletes. Their forms were twisted by the sea, but they still had that classical grace. Marble sculptures, too, likely copies of famous Greek originals, delicate glass bowls, ceramics. Even personal items, a bronze couch leg shaped like a sphinx, and coins. The coins were the key. They dated the whole disaster. They pointed to a voyage sometime between 70 and 60 BCE. This was no ordinary merchant ship. It was Roman, almost certainly heading from the Greek east back to Italy, and its cargo looks like loot, systematic high-value loot, the kind a Roman general would amass, or a wealthy aristocrat. After a military campaign or a buying spree through the plundered cities of the Hellenistic world, the mechanism wasn't packed with tools, it wasn't with trade goods. It was nestled among art, among luxury, and that changes how we see it. It wasn't a scientist's personal instrument carefully carried. It was a prize, a trophy of knowledge, a testament to Roman desire for all things Greek, not just their art but their intellect, captured in a box. Scholars have even floated a name, a tantalizing one. The timeline coincides with a figure famous for his appetite for Greek learning, for his vast personal collections, Julius Caesar. Could this have been part of a shipment for his villa, or for a fellow Roman elite like Cicero who wrote so admiringly of such devices? We can't know for sure, but the possibility fits. It paints a scene. In a lavish Roman villa, a guest might admire a bronze statue in the garden, then be ushered inside to witness an even greater marvel. A machine that moved with the logic of the heavens. The mechanism was the ultimate conversation piece. It demonstrated not just wealth but a sophisticated understanding. The cargo does more than suggest a wealthy owner. It helps us date the mechanism's creation. Since the ship sank around 60 BCE, the device must have been built before that. It places its manufacture in the late Hellenistic Golden Age, perhaps around 100 BCE. When the workshops of Rhodes or Alexandria were at their peak, and the trade route is a clue. This was a transfer of technology, but not in the way we think. It wasn't a blueprint being shared. It was a finished product, a black box of genius, being physically transported from the creative centers of the Greek world to the new imperial power of Rome. The ship's journey maps the flow of ideas at the end of an era. Carried the last brilliant embers of one civilization as cargo to the hearth of another. And in the dark water off, that transfer was frozen in time, leaving us to wonder what other seeds of knowledge were on board, seeds that never reached their destination. The ancient world had brilliant minds and brilliant tools, but nothing else we've found is like this. The Babylonians, for centuries, their astronomers tracked the heavens. They wrote it all down on clay tablets, sophisticated tables. They could predict planetary positions, predict eclipses using complex arithmetic. But those predictions were done by hand. The tablet was a record, a result. It wasn't a machine that did the calculation. It was brilliant but static. Then there's the Greek astrolabe, a beautiful brass instrument. It came a few centuries after the mechanism was lost. It was a two-dimensional model of the sky, A star chart you could rotate. You could tell time, find stars, solve navigation problems. But its mechanics were simple. A few moving parts on a plate. It was a superb tool, but it didn't compute. It didn't model the moon's irregular motion or the planets through an internal gear train. It was a map, not a simulator. Look east to ancient China. Innovation flourished there. Around 130 CE, built it to detect earthquakes. He built complex water-driven armillary spheres, models of the celestial sphere, monumental achievements. But these elaborate astronomical clocks appear in the record centuries after the mechanism was underwater. They represent a different flowering of mechanical genius. Later, powered by water, not precise hand-cranked gears. So when you put the device beside its contemporaries, its isolation is stark. In the classical Mediterranean world, it has no peers. No other geared device of that complexity has been unearthed from that era. It synthesized astronomical theory with precision mechanical engineering in a way that wasn't replicated. For over 1,000 years, the technological high-water mark it represented wasn't reached again. That's what makes it a singularity. A lone data point so far off the chart it forces you to redraw the whole graph of ancient innovation. It wasn't the next step on a ladder. It was a leap into thin air, and for 1,500 years, no one else jumped. The knowledge built into that device is written in its metal. The cycles it calculates so perfectly, the Seros, the Metonic, those weren't Greek discoveries. They came from the East, from Babylonian astronomers. For generations they sat in their temple towers recording everything on clay tablets, planet movements, every eclipse. They were building a database centuries long of what the sky did. Their aim was divination, reading the gods' will, but their method was pure observation. Over generations they saw the patterns. They found the eclipse cycle about 18 years and 11 days, the Seros. They defined the 19-year Metonic cycle, aligning the sun and moon calendars. This was data-driven science long before the term existed. Then Alexander's conquest opened up the Hellenistic world. That treasure of Babylonian records became available. A thinker like Hipparchus on Rhodes in the 2nd century BCE, he didn't start from zero. He had these centuries of observations. He could analyze them, refine the cycles, build his geometric models of the cosmos on that foundation of data. The mechanism is the final product of that collaboration. Its bronze gears turned by Babylonian arithmetic, cycles refined by generations of Eastern scribes. But the physical form, turning those cycles into a system of interlocking gears, that was Greek geometry, Greek mechanical craft. It's a hybrid object. Eastern empirical knowledge given a Greek mechanical body. This wasn't just borrowing, it was a fusion, something neither culture could have made alone. The mechanism stands at a crossroads. When trade routes empires bring different ways of thinking together, something new can emerge. The Babylonian way was about recording numbers, finding patterns in time. The Greek way was about building models in space, understanding the geometry of motion. The mechanism does both. It takes the Babylonian time cycles and makes them visible as a moving geometric model. It captures a moment fleeting where two intellectual traditions met and sparked a leap in technology. It reminds us that revolutionary ideas rarely come from isolation. They come from connection, from borrowed insight, from looking at an old problem through a lens made by another civilization. That bronze machine is a philosophical argument. The act of building it reveals a worldview. You look at the sun, the moon, the planets, these brilliant distant lights, as gods but to see them not as divine caprice but as a system of interlocking motions, and to believe that system could be understood, measured, and then recreated with tiny gears in a wooden box. That's a radical leap of thought. It suggests the Greeks who made this saw the cosmos in a mechanistic way, a clockwork universe, long before clocks as we know them even existed. The idea that nature follows predictable mathematical laws, that's the bedrock of modern science. We usually trace it back to Galileo, to Newton, centuries later, but the mechanism places that seed of thought over 1,000 years earlier. It was built on the work of astronomers like Hipparchus, who used geometry to model the heavens. The mechanism takes that geometry and makes it physical. It proves the theory by turning a crank. Each time those bronze gears mesh, they assert a powerful idea. The universe is not chaotic, it is orderly, it is comprehensible, and if it is comprehensible, it can be predicted. This challenges an assumption about the ancient mind, that they saw the heavens as purely the realm of gods, unpredictable, beyond human understanding. Clearly, for the makers of this device, that wasn't the full story. They saw divinity perhaps in the order itself, in the magnificent repeating cycles. The mechanism doesn't deny the sacred. It finds the sacred in the pattern, in the mathematics. So the device is a profound statement. A statement made not in words but in craftsmanship. It says that human hands and human minds can replicate the logic of the cosmos. We can build a mirror for the universe, and that mirror will tell the truth. This embedded a materialist perspective into Greek thought, a practical philosophy, one that valued observation, calculation, tangible proof. The universe operated by knowable rules, and those rules could be captured here, in this world. In metal and wood, that perspective is what makes science possible. So when we look at this corroded relic, we're not just looking at an ancient calculator. We're looking at the birth certificate of a powerful idea. The idea that reality has a structure we can decode, and that decoding doesn't distance us from wonder, it deepens it. To know the intricate dance of the moon, to build a machine that performs that dance, that is to participate in something magnificent. The mechanism is a bridge. It connects the human scale of a turning handle to the cosmic scale of orbiting worlds, and in doing so it tells us something. The desire to understand, to model, to hold a piece of the universe in our hands, that desire is ancient. It is part of what makes us human. The mechanism didn't just predict eclipses, it predicted the very possibility of a universe we could ever hope to understand. But the story of this device didn't just end in a museum drawer. It got out. It escaped the world of academia and caught fire in the public imagination. You see it now in best-selling novels, in major documentary series. It's a central mystery in popular video games. The mechanism became a star in its own right. And that cultural journey usually starts with one simple question. How could the ancients have built something so advanced? That question opens the door to a lot of speculation. The mechanism shows up a lot in conversations about out-of-place artifacts. People point to it. Theories about lost civilizations or ancient astronauts use it as supposed evidence. But the actual scientific investigation, the work done over decades, tells a different story, a more compelling one. Its origins are thoroughly human, wonderfully human. It's not a sign of alien intervention, it's a testament to human ingenuity. To a specific, brilliant moment in history. And that popular fascination isn't wrong, really. It's reacting to the same other researchers feel. This was a genuine historical mystery, and it was solved, piece by piece. What it revealed wasn't a supernatural secret. It was a forgotten chapter of human achievement. It has this power to rewrite the story we tell ourselves about technology. That's profoundly exciting. It appeals to our love for a great puzzle, one with real gears. Real genius behind it, and this cultural footprint has real effects. Museums around the world display beautiful working replicas now. Artists create visualizations of its internal cosmos. Modern engineers build their own versions. There's a connection there across, a shared craftsmanship. That broad engagement is important. It acts as a gateway. It brings the advanced history of science to people who might never open an academic journal. Someone watches a documentary. Or a player finds a virtual model in a game, and suddenly they're introduced to Hipparchus, to Hellenistic engineering, to the idea that the ancient world was capable of mechanical computation. It sparks a curiosity, one that can lead down countless rabbit holes. History, astronomy, archaeology. So the mechanism does more than predict celestial cycles. It inspires. It reminds a global audience that the drive to map the stars, to build machines, to unravel the universe, that's not a modern invention. It's a timeless human trait. That bronze box from the Shipwreck is still on a journey. It's not ticking in a scholar's hand anymore. Now it's firing synapses in minds all over the planet. And maybe its greatest legacy is just that, proving that the wonder of discovery is as relevant today as it was 2,000 years ago. The CT scanner told us a lot. But not everything. And now the next part of this story is happening in labs and down on the, with tools that would look like magic to the people who built the thing. The mechanism, that story isn't done. It's a puzzle with pieces still missing, and the way we're looking for them is more advanced than it's ever been. So the future of this research, it depends on a new kind of imaging. Think about the X-ray tomography that showed us the gears inside for the first time. Now imagine that, but with much higher resolution. Techniques like phase contrast X-ray, advanced photogrammetry, they can see deeper into the corrosion. They might show us inscriptions that are completely invisible now, a single faded letter, the ghost of a gear tooth pressed into the crust. A tiny detail like that could confirm the exact layout of the planetary gears. It could be the final piece of the model. Every new scan is like cleaning a dirty lens, bringing a 2,000-year-old blueprint into focus. And at the same time, the search goes back to the water. Back to marine archaeology has changed since those sponge divers went down. Now it's robotic submersibles. They have sonar arrays, delicate arms. They're going over the wreck site, sifting through sediment that's been sitting there for. The hope is that another lump is down there, bronze and wood in the silt. Maybe it's a missing fragment from the main device, a gear that proves a theory, or maybe it's something else entirely, a different mechanism. Was this ship carrying a whole shipment of them? A delivery of intellectual marvels to some Roman patron? Every dive is an act of faith, a belief that the sea hasn't given up all its secrets. Then on land, the work turns to texts. Scholars are going back to classical writings, Cicero, Roman engineers like Vitruvius, and they're asking a new question. Now that we know this device existed, what else might be describing it? A passing mention of a moving sphere, a bronze calculator. Those phrases mean something different now. The mechanism is like a physical reference, a stone. It lets us read between the lines of history, looking for echoes of a lost technology in poetry, in philosophy, in technical manuals. But maybe the biggest thing this object does is change how we look at the past. The mechanism forces a shift. It makes scientists and historians look for evidence of complex technology in places they might have ignored before. It makes us re-examine other mysterious artifacts from antiquity. Could there be geared systems in other cultures? Does this suggest a broader tradition of mechanical instruments, one that's vanished now? The mechanism teaches a kind of humility. That our ancestors' capabilities might have been much greater than the broken archaeological record usually shows. It tells us to keep our minds open, to look for sophistication in unexpected places. The next discovery might not even come from Greece. It could come from a Mesopotamian clay tablet, a mathematical formula that matches a gear ratio perfectly, or from studying an Egyptian water clock, finding a precursor to precise mechanics. The mechanism has broken a seal. It's opened up a forgotten world of innovation. It's given us permission to look for the ghosts of other machines, the echoes of other leaps of genius that time tried to erase. So the search keeps going. Not just for more bronze pieces, but for a deeper understanding of how high ancient ingenuity could really reach. That bronze machine is a question we're still trying to answer. It's more than a museum piece, it's a signal fire, lit 2,000 years ago and we can still see it burning. Its light shows us something about ourselves, about human curiosity, about what the mind can do. These gears, modeling the cosmos, they make you reconsider. Scientific progress isn't a straight line. It isn't just primitive to advanced. It has peaks and valleys, summits that are reached and then sometimes forgot. The Hellenistic Greeks were on one of those summits. They looked at the stars and saw more than myths. They saw mathematics, and they had the skill to build a model of it. That achievement makes you acknowledge how sophisticated they were. A sophistication our own history had erased. The mechanism is a lesson. It's about the fragility of knowledge. Great understanding isn't a permanent possession. It can be lost, to the sea, to fire, to changing priorities. That one shipwreck held a library of engineering, and for 1,000 years that library was closed. Its existence is an inspiration, a call to preserve what we discover, to build on it carefully. The insights we have now are precious. They connect us to the future and to a past that was far more capable than we thought. Today we point telescopes at galaxies. We send probes to the edge of the solar system. We're standing on the shoulders of those thinkers. We're continuing their quest. We mapped the galaxy with silicon, where they used bronze and deduction. Their legacy isn't just in the gears we found. It's in the act of looking up, of daring to understand.